Alright, so in this lecture we're going to talk a little bit about friction. Okay, and what friction is it's a force that opposes motion at a contact surface. So when two surfaces are in contact, it's that force that opposes motion at that surface. So if we look at a block like I have here, okay, and without any forces applied, I would just have the weight down and a normal force up. Okay, the second I start applying a horizontal force, assuming this again is sitting on a surface like the ground. Okay, the second I apply a force at P, to keep that thing in equilibrium, I have to create some sort of force, and that force is the friction force, again occurring at the surface in the opposite direction of the applied force. Okay, and to keep it in equilibrium, that friction force has to equal that applied force P. Okay, but now what happens here is I create a couple moment. Okay, because these two forces are equal, opposite, and separated by a distance h. So in order to keep it in equilibrium with regards to moments, my normal force has to shift over some amount x to create a couple moment with the weight here, to create a balancing couple moment here, to keep that in equilibrium. So when I apply this force P, I create a friction force in the opposite direction, and I shift my normal force over in order to balance out the moments. Okay. Now, when I get to the point, okay, where I have impending slipping, this is the point right before this block starts moving. Okay, I'm at basically my maximum friction force. This is the maximum force that the friction can hold. Anything more than this, friction can no longer hold it, and it'll start slipping. Okay, and that maximum friction force is defined as mu s times the normal force, where mu s is the coefficient of static friction. So the larger that coefficient of static friction, basically the stickier the surface contact is, and therefore the greater force that friction can hold. Now don't confuse this with the static friction force, right? This force only needs to be as big as P, and it increases as P increases, okay? But then right before this thing starts slipping, okay, is where I'm at that maximum friction force. Any bigger applied force and this thing's going to start slipping. So it's a maximum force, not a static force. Okay. So at this point we have defined what we call a static friction angle. That static friction angle is basically the angle that's made for the resultant moment, which is essentially the normal force plus the friction force. And we'll actually use this a little bit later when we talk about screws. Okay, and that friction angle is simply the inverse tangent of the friction force, the maximum friction force, over the normal force, which of course the maximum friction force is mu Sn. Okay, my normal forces cancel, and I can find my static friction angle as just a function of the coefficient of static friction. Okay, so this is the maximum friction force. This is the force that friction is able to hold. It's not necessarily what friction is. Friction is, if it's in equilibrium, that friction here is balancing that force P, okay, until I reach this maximum friction force and slipping occurs. Now, I can have another type of motion that could occur. I could have tipping, okay, and right before this thing starts to tip, my normal force here is over here at the edge, okay. Any more, if I apply any more force and create a larger couple moment between P and the friction force, then N has to move over, and there's no more place for N to go. Therefore, this thing has to tip over. So right before this thing starts to tip, N is essentially over here at the corner. Okay. Any more than that, if N starts moving over here, this thing is tipping over. Okay, and it's the last amount that it can hold. Okay, so that's another type of impending motion. Now, if slipping occurs, okay, if I get slipping motion, okay, after I've broken through that maximum friction force, okay, the friction force then becomes constant, okay, and it's still a mu times a normal force, but now I have mu k, which is the the coefficient of kinetic friction to create that friction force, okay, and that is always going to be less than my static friction force. If you think about trying to move like a heavy box or something on it, okay, it actually takes more force to get that thing started moving. Once it's moving, then you want to keep it moving because the friction force is less than the force needed to get it to start moving. So that maximum friction force is going to be bigger than the kinetic friction force. So here's a little plot of what happens. So let's take for this example here. I start applying P. I start at 0 and I slowly ramp it up. Okay, so as P increases, my friction force increases, and it's basically, that friction force equals the applied force for this situation here. Okay, and as I increase P, F increases with it, still increasing until I get up to this point here. At this point right here, that friction force can't hold it anymore. I'm at my maximum friction force. Okay, I'm at mu S N right here. Okay, that's the maximum. If I continue to apply friction beyond that, if I continue to apply a force P beyond that maximum friction force, what happens is I get this drop down and I go at kinetic friction, constant until I get to very high forces. But for our purposes, we'll just assume the kinetic friction force is always constant at mu Kn. Okay, so again, I've got that maximum friction force. After I go beyond that, it drops down. If I go below that, the friction simply equals the applied load. All right, so how do I solve problems with friction? Okay, well, the first is to draw a free body diagram. And you may have to draw more than one depending on if you have more than one body. Okay, at this point, when you first draw the free body diagram, make no assumptions about the friction. Okay, do not assume that friction force equals mu times n. Okay, just draw it up there as F and move on. Okay, then you go ahead and write your equilibrium equations. Okay, just using friction, make no assumptions about friction at this point. Just write out the equilibrium equations just like we always have. Okay, then take a look. Okay, do I have enough equations to solve the problem? If I don't, if I have too many unknowns, now I need to make an assumption. Now this assumption is going to have to be proven later. So I have to make an assumption about friction. Okay, I can either assume that the body is about to slip, at which point the maximum friction force, okay, the friction's at its maximum, right? If it says, hey, how much force is it going to take to get this thing to move? If you assume that the motion is slipping, okay, then you have to say, hey, that maximum friction force, or that friction's at its maximum friction force. You could also assume that it's tipping. Okay? And at that point, you basically just move the normal force over to the edge and say, okay, that's where that's located, basically giving that its location, and you use that assumption. Now, if you have enough equations, you just go ahead and solve them, and then you're going to make sure that the friction stays on there. Okay? So you only make an assumption if you don't have enough equations. Okay, now you should have enough equations, either because you had enough to begin with, or you made an assumption about the friction giving you one more equation. Okay. After you solve the equation, then you have to determine whether or not your assumption is correct, whether or not the friction is feasible. Okay. You have to make sure that friction is less than the maximum friction. Okay. Unless, of course, you made that assumption. Okay. So if you assumed it's tipping, you've got to make sure that it didn't slip. Okay. Or in the case where you could solve without making any assumptions, you still have to make sure that the friction holds. Okay. You also have to make sure that n is on the base. Of course, if you assume tipping, you've made this assumption. Okay. This mainly occurs when you assume slipping. If you assume slipping, you have to make sure that n is in the location it wants. Or if you made no assumptions, you had enough equations initially, you have to make sure that normal force stays on the base so that the object actually is in equilibrium. Okay, so really doing problems in these friction problems, a lot of times you're making assumptions and then going back and proving them. Okay, so go ahead and check out the example, and hopefully that'll help drive through a lot of this procedure.